What if the most terrifying truth about existence is not death, nor the emptiness of space, but the possibility that reality itself may be a trick? For centuries, human beings have trusted their senses, believing that what we see, touch, and hear corresponds to something stable, external, and absolute. A stone on the ground, a mountain on the horizon, the sound of rain. These were taken as proof that reality is solid. Yet in the laboratories of the 20th century, physicists uncovered a riddle so deep, so unsettling, that it continues to defy explanation today. The very act of observing the world seems to bring it into being. Until it is measured, until it is witnessed, reality exists in a blur of possibility. This is not philosophy. This is quantum physics. The riddle begins with an experiment first conceived more than 200 years ago. In 1801, the English scientist Thomas Young performed what he called the double-slit experiment. He passed light through two narrow openings and watched as it painted a delicate pattern of bright and dark bands on the screen beyond. It was the signature of waves, ripples interfering, peaks amplifying peaks, troughs canceling troughs. This was unremarkable at the time. Everyone knew light behaved as a wave. But decades later, when scientists learned that light was also made of particles, tiny quanta called photons, the old experiment took on a new darkness. If light is made of individual particles, then each one must go through one slit or the other, not both. And yet, when repeated with single photons, the interference pattern still appeared. Each photon behaved as if it had traveled both paths at once, splitting into overlapping shadows of itself, and then choosing a single destination only at the moment of detection. It is here that the paradox sharpens. When no one looks, reality spreads itself thin, like ink dissolving in water, each possibility coexisting. But the moment a detector is placed to spy on which slit the photon travels through, the interference vanishes. The photon is forced to commit, slit 1 or slit 2, but not both. The presence of observation collapses possibility into certainty. But why? What does it mean for the universe to behave one way when unseen and another way when observed? For physicists like Niels Bohr, this was not just a puzzle of optics, it was a revelation about the nature of existence itself. John Wheeler, the American physicist, took the experiment even further in the 1970s, proposing what he called the delayed choice experiment. Imagine, he said, that the photon has already passed the slits, already on its way. At the very last instant, we decide whether to measure its path or not. Common sense insists the past is fixed. The photon must have already chosen. But in Wheeler's version, the outcome still depended on the last-minute choice. If we watched, the photon behaved like a particle, if not like a wave. It was as if the act of observation reached back in time and rewrote history. Wheeler himself declared, "No phenomenon is a phenomenon until it is observed." This idea that the present could rewrite the past is almost unbearable to the human mind. It suggests that reality is not a completed film reel but a script waiting for actors, collapsing only when the curtain rises. In 2007, Australian physicists performed Wheeler's experiment with single photons, using sophisticated beam splitters and detectors, and the results confirmed the bizarre prediction. The universe seemed to decide retroactively what the photon had done, as though reality itself refused to be nailed down without an observer. Consider the implications. If the universe exists only when observed, then who or what is doing the observing? When you close your eyes at night, does your bedroom dissolve into a fog of probabilities? Do distant galaxies exist only when astronomers point their telescopes toward them? This unsettling possibility is known as the observer effect. At its core lies the suggestion that reality may not be independent of consciousness, but instead intertwined with it. Many physicists resist this interpretation, insisting that observation is simply any interaction with the environment, not human awareness. Yet the mystery remains. Why should nature play this game of hide and seek at all? It was to dramatize this absurdity that Erwin Schrödinger in 1935 conjured his famous thought experiment, the cat in the box. Inside, a radioactive atom may or may not decay within the hour. If it decays, a mechanism shatters a vial of poison and the cat dies. If it does not, the cat lives. According to quantum theory, until the box is opened, the atom exists in a superposition of decayed and not decayed, and therefore the cat must be both alive and dead at the same time. Schrödinger meant this as a critique, a parody of how ridiculous quantum mechanics appeared when stretched to the macroscopic world. Yet experiments in recent decades have created superpositions not of cats, but of molecules large enough to be seen with microscopes, vibrating in two places at once. The cat, once meant as satire, is now a haunting metaphor for the genuine weirdness of our world. Albert Einstein, never comfortable with quantum strangeness, called it incomplete. He proposed in 1935 with colleagues Podolsky and Rosen that particles might possess hidden variables, unknown properties that predetermine their behavior. He rejected the idea that a photon could be in two states at once, insisting instead that it only seemed uncertain because we lacked the full picture. But John Bell, in 1964, showed mathematically that if hidden variables existed, their effects could not match the predictions of quantum mechanics. Decades of experiments since then have confirmed Bell's theorem. The universe does not follow Einstein's intuition. Entangled particles, separated by vast distances, behave as if they share a single existence, collapsing into correlated states instantly when measured. Einstein derided it as spooky action at a distance. But the spookiness turned out to be real. Pause and reflect. If particles across the universe can influence each other instantly, faster than light, what does this say about space and time? What does it say about reality itself? Physicists still debate the meaning. Some embrace the Copenhagen interpretation. Reality does not exist in a definite state until measured. Others champion the many worlds view. Every possibility branches into a parallel universe, and the observer merely finds themselves in one branch. Still others turn to the simulation hypothesis. Perhaps the universe operates like a vast computer, rendering detail only when called upon by observation, conserving its resources in the process. Yet none of these interpretations erases the paradox. They only cloak it in different myths. The underlying fact remains. Experiments prove that particles do not behave as solid, real things until measured. Reality is not the stone wall we once believed, but a shimmering mirage, dependent on context, collapsing into shape only under the gaze of observation. And so we are left with questions that gnaw at the foundations of sanity. Is reality real when unobserved, or does it remain a ghostly wave of potential, awaiting an audience? When no one looks at the moon, does it still hang in the night sky, or does it slumber in a haze of probabilities until an eye turns upward? Does consciousness itself hold the power to carve the universe from possibility into fact? Or are we all simply illusions within a grander, hidden machinery we cannot yet see? The story of quantum strangeness does not end with the double-slit experiment. If that was the first crack in the glass of reality, then entanglement was the shattering blow. Imagine two particles born together, like twins separated at birth. They fly apart at incredible speeds, perhaps across a laboratory, perhaps across light years of empty space. According to classical reasoning, once separated, they should live independent lives. One might spin clockwise, the other counterclockwise, each carrying its own destiny. But quantum mechanics denies such neat divisions. Entangled particles remain bound by a thread invisible to space and time. Measure one, and the other instantly reveals its state, no matter how far away. The universe seems to whisper to itself across the void, faster than light should allow. Einstein despised this. He called it Spukhaft-Fernwirkung, spooky action at a distance, and argued it was proof that quantum mechanics was incomplete. Surely the particles carried hidden instructions, like two playing cards face down, already determined before the dealer lays them on the table. But in 1964, John Bell struck a blow to this hope. Bell derived a theorem showing that if the world were ruled by hidden variables, then the correlations between entangled particles would obey strict statistical limits. If those limits were violated, then no hidden instructions could explain the results. Nature would have to be non-local connections weaving across reality beyond space itself. The test was not easy. It required detectors, single photons, precise timing, all technology unavailable in Bell's day. But in the 1980s, Alain Aspect and his team in France finally performed the experiment. The results? Quantum entanglement violated Bell's inequality exactly as predicted. No hidden variables could save Einstein's dream of a local, objective reality. The universe was indeed spooky. Since then, entanglement experiments have grown ever more precise. In 2015, scientists in the Netherlands performed a loophole-free Bell test with entangled electrons across 1.3 kilometers, and again, the results defied classical explanation. Reality, it seemed, was not local at all. Now pause and imagine the consequences. If the act of measuring one particle here instantly shapes the state of its twin over there, then distance itself is not what we thought it was. The separation between points in space may be an illusion, like a reflection in a mirror, vanishing the moment you reach for it. Could it be that everything in the universe is secretly entangled, stitched together by an invisible fabric? If so, perhaps individuality is a trick. Perhaps you and I, stars and stones, are not separate beings at all, but branches of one infinite whole, hiding our unity beneath masks of matter. And yet, even this unity does not solve the riddle of observation. What decides when possibility becomes reality? Is it the measuring device, the conscious mind, or something deeper? In 1961, Eugene Wigner posed a question so haunting that it still divides physicists. Imagine, he said, a friend performing a quantum measurement inside a sealed lab. From the friend's perspective, the result is definite. The cat lives or dies, the photon passes slit 1 or slit 2. But from Wigner's perspective outside the lab, the entire system, including his friend, is still in superposition. The friend is both aware of one outcome and the other, suspended in a strange half-life until Wigner opens the door. Reality itself becomes relative. What is true for one observer may not be true for another. This paradox, now known as Wigner's friend, suggests that the collapse of possibility into certainty may not be universal at all. Instead, it may depend on the perspective of the observer. In 2019, a team of physicists in Austria and Canada performed a version of Wigner's thought experiment using entangled photons. The results hinted that different observers could indeed experience different realities simultaneously. If this holds true, then reality is not a single story, but a chorus of conflicting voices. What you call real may not match what I call real, and both may be equally true. Truth itself becomes fragmented, contextual, perhaps even meaningless. Consider how far we have drifted from the solid ground of common sense. Once, we thought the universe was a clockwork, gears and cogs spinning predictably. Now we find ourselves in a hall of mirrors where particles occupy many states at once, where observers may disagree on what is real, where distance dissolves into illusion. What is left to hold on to? Some physicists turn to the many worlds interpretation, first proposed by Hugh Everett in 1957. In this view, the wave function never collapses at all. Every possibility becomes real, but in different universes. In one branch, the cat lives. In another, it dies. In one, the photon takes the left slit. In another, the right. The universe is not a single stage, but an infinite theater, every script performed simultaneously, with you and I drifting endlessly through branching realities. It is an audacious vision, almost impossible to imagine, yet it carries its own unsettling weight. If all outcomes exist, then what is the meaning of choice? If every decision you make spawns countless copies of yourself living out every alternative, then what does it mean to be you? Is identity itself just another illusion, one branch among billions, indistinguishable from its twins? And so the question deepens. If the world is not local, if reality is not singular, if observation itself is unstable, what then anchors existence? Is there some hidden structure, some foundation beneath the quantum fog? Or is the fog all there is? A dream unfolding without dreamer, waiting only for the next act of attention to give it shape? The double-slit experiment was unsettling enough when it showed us particles behaving like waves, reality flickering between certainty and possibility depending only on whether we watched. But scientists, being both courageous and restless, wanted to press harder. What if you could not only decide whether to watch but also delay that decision? What if you could make your choice after the particle had already crossed the slits? Would reality remain firm, or would it bend backward, rewriting itself to match your gaze? This question gave birth to what is called the delayed choice experiment, imagined by John Archibald Wheeler in the late 1970s. Wheeler suggested that whether a photon behaves like a wave or a particle could depend on a measurement made after it had already entered the apparatus. If that sounds like science fiction, remember, in the quantum world, strangeness is the norm. When physicists tested Wheeler's idea decades later, they found his wild intuition was right. The act of observation appeared to decide not only the photon's present state but also its past behavior. The photon had already passed through the slits, and yet the choice to measure it after the fact seemed to alter the record of what had already happened. But even that was only the beginning. In the 1990s, physicists extended Wheeler's vision with something even more haunting: the quantum eraser experiment. Imagine firing photons through the two slits as usual. On the far side, instead of simply striking a screen, they are sent through a system that can mark or tag each photon according to which path it took. With the path marked, the interference pattern disappears, and the photon behaves like a particle. Reality chooses a single line of travel. But here lies the marvel. If the which path information is erased, if the tag is removed, even after the photon has already traveled, then the interference pattern returns, as though the photon had never been forced to decide. It is as if reality itself can be rewritten, the past undone, possibility restored. Even more extraordinary is the delayed choice version of this eraser. The experimenter can decide to erase or preserve the photon's path information after the photon has already been detected, and still the outcome shifts accordingly. The decision in the present appears to ripple backward, sculpting the history of the particle. How can this be? One interpretation says that time, as we understand it, is not fundamental. Past, present, and future may be woven together in a single tapestry, so that a change in one thread resonates across the whole fabric. Others argue that what is truly being rewritten is not the past itself but our access to information about it. In this view, reality is less like a solid landscape and more like a storybook that does not reveal its plot until the reader decides which page to turn. Pause to let that sink in. The world we inhabit, the ground we trust, the minutes that seem to tick forward in a steady march. What if they are not as firm as we believe? What if your choices today could echo backward, sculpting yesterday's reality in ways you cannot directly perceive? Science does not yet give us a final answer, only equations that predict the outcomes, and outcomes that leave us shaken. There is another way to think of it. Perhaps the universe does not carry a single history. Perhaps instead it carries countless ghost histories, half-formed and incomplete, awaiting the decision of the observer. In one history, the photon travels through the left slit, in another through the right, in yet another through both. And the history that becomes real is only the one compatible with the questions we later choose to ask. The rest fade away like mist in the morning sun. If this is true, then the past is not a frozen stone but a living fog, reshaped by every act of measurement, every choice of curiosity. What does this mean for us, creatures of flesh and memory? If time can bend, if the past can be revised, what then becomes of history? Is memory itself a kind of quantum record, fragile and incomplete, collapsing into certainty only when we summon it? Neuroscience hints at this possibility. Memory is not a static archive but a process of reconstruction, altered each time it is recalled. Could it be that the frailty of memory mirrors the frailty of reality itself? That both are stories written in water, never fully fixed until we choose to read them? Some philosophers seize on this and dare to connect it to free will. If the future can influence the past, then the chain of cause and effect is not as unbreakable as we once believed. Choice may ripple across the timeline, not merely forward but backward, shaping the stage on which it will later act. Does this grant us freedom, or does it erase freedom altogether, trapping us in a web where every choice is already reflected across time? The quantum eraser does not answer, yet it forces us to ask. And so, with each layer of experimentation, the paradox only deepens. The double slit shattered the illusion of a solid world. Entanglement shattered the illusion of separation. And now, the quantum eraser shatters the illusion of time itself. Past, present, and future may not exist as separate realms, but as aspects of a whole too vast for us to comprehend. The arrow of time may be no arrow at all, but a circle or even a sea where events ripple in both directions. And if that is true, then what are we? Beings of flesh and bone, yes, but also beings of narrative, sculpted not only by our past but by futures yet unseen. Each act of perception, each act of choice, reshapes the world not only ahead but behind. And perhaps this is why reality feels so fragile, so fleeting, so dreamlike, because it is, in truth, a dream being written as we live it. The deeper we stare into quantum paradox, the more fragile the world appears. We began with particles behaving like waves, then discovered that entanglement dissolves distance, and finally saw that even the past is not safe from the eraser's touch. Reality flickers like candlelight, trembling between stories, awaiting the next act of observation to decide what it was and what it will be. And now, standing at the edge of this abyss, one final question presses itself upon us. If the universe behaves like information, fragile and malleable, then could it be that reality is not a thing at all, but a computation? Physicist John Archibald Wheeler once wrote the phrase "it from bit." By this, he meant that the essence of the physical universe arises not from matter, but from information. The fabric of reality is not stone or clay, but binary choice. Yes or no, observed or unobserved. Each particle is not a piece of substance but a digit in the great cosmic code. And as experiments grow stranger, this idea no longer sounds like philosophy alone. Quantum mechanics behaves as if the world is rendered only when we ask for it, as if existence is on demand, like the pixels of a screen. Think of a video game. The computer does not render every mountain, every sky, every grain of sand all at once. It only renders what the player can see, conserving resources. Is it possible that our universe works the same way, rendering reality when and where it is observed, leaving the rest in shadowy probability until it is needed? This would explain why measurement is so central, why possibility collapses only when observed. Perhaps the universe does not exist in fullness until consciousness calls it forth. The simulation hypothesis has gained traction not only among philosophers but among scientists and technologists. If quantum mechanics tells us that reality is inseparable from information, then perhaps information is all there is. Could the entanglement of particles, instant and timeless, be nothing more than the rules of a program, shortcuts coded into the architecture of existence? Could the rewriting of the past be no more mysterious than a computer re-rendering a scene when the player's perspective changes? The thought chills us, yet it explains so much. But if this is a simulation, who or what runs it? Some imagine advanced civilizations, billions of years ahead of us, running ancestor simulations of their past. Others imagine intelligences beyond our comprehension, creators whose motives we cannot guess. Still others see in this the shadow of ancient myths, that what religions called the divine, science now rediscovers as the programmer. Yet whoever or whatever stands behind the code, the consequence for us is the same. Reality is not solid. It is a lie, a mask, a curtain drawn over something deeper. And if reality is a lie, what then are we? Avatars in a game? Characters in a story? Or something stranger still, beings of consciousness temporarily woven into the fabric of the code, dreamers within a dream? If consciousness itself collapses the wave function, then perhaps we are not players at all but co-authors. Perhaps the code does not exist without us, and our act of observation, our act of living, is part of the program's execution. Consider the implications. If the world is information, then death is not erasure but deactivation, the shutting down of a process. If the past is mutable, then memory itself is not record but reconstruction. If the universe is rendered only when observed, then the stars that glitter above you tonight may not exist until you lift your eyes to see them. You are not only a resident of reality, you are its engine, its witness, its essential participant. Without you, perhaps nothing exists at all. And yet, even this revelation does not soothe the unease. For if we live in a simulation, if reality is a lie, then truth may forever escape us. The double slit will whisper in one ear, entanglement in the other, the quantum eraser behind our back, and still the riddle remains. What is real? Perhaps there is no answer. Perhaps the purpose is not to solve the riddle but to live within it, to embrace the uncertainty, to feel the wonder and the terror of existing in a world that is both dream and machine. In the end, we return to where we began, the question of what is real when we are not looking. Physics has shown us that the world is not as it seems. The ground beneath our feet trembles with possibility. Time itself bends under the weight of our choices. And reality, the solid stage upon which we live our lives, reveals itself to be nothing more than a fragile mask, a performance unfolding at the moment of observation. So tonight, as you close your eyes, ask yourself, when you are no longer watching, what remains of the world? Does it fade into a haze of probability, waiting to be summoned? Does it continue without you, indifferent and eternal? Or does it collapse into nothingness until your gaze calls it forth again? The truth may be forever hidden, but perhaps that is the final lesson of the quantum paradox. That reality is not given to us, it is made with us. And in that fragile dance between observation and existence, we may glimpse the closest thing to truth we will ever know.